All right, let's just dive right into this explainer. Today, we're going to essentially reverse engineer that incredible machine sitting right there on your desk. I mean, we literally live our entire modern lives through these glowing portals, right? But it's just so easy to take them completely for granted. So we're looking under the hood. And not just looking at the wires or the microchips, but the actual fundamental concept of computing itself. We're going to trace the logic that powers our entire modern world all the way back to its very earliest, clunkiest, mechanical roots. Seriously, think about it for a second. You spend hours staring at this thing every single day. You type, you click, you scroll, and boom, the machine responds instantly. But how exactly does it think? You know, we interact with the physical stuff, the smooth glass, the clicky keys, but the real magic, the actual brain power, is the invisible logic running underneath. To truly grasp what a computer is, we really need to understand the fundamental problem it was actually built to solve in the first place. Let's start with what we all know, right? The modern setup. You've got hardware and software working together in this perfect, seamless synergy. You have the central system unit basically acting as the brain, paired up with your monitors and all your input peripherals. And yeah, it looks incredibly complex, and, well, it is. But if we strip away all those flashy graphics and the internet connectivity, what is the system actually doing at its absolute core? Well, the true definition is actually surprisingly simple. The word computer literally just comes from compute, which means to calculate. That's it. That is its absolute foundation. So underneath all those ultra-sleek interfaces and heavy video games, it is essentially just a hyper-fast electronic calculator. It just accepts data, crunches the math, and spits out a result. Okay, let's move on to the next section, the 5 superpowers of computing. So you might be wondering, if it's really just a calculator, why on earth does it rule the world? Well, according to the source material, there are 5 defining characteristics, let's call them superpowers, that elevate computers way beyond your basic pocket calculator. First up is speed. We're talking processing data at literally millions of instructions per second. Then, pair that with accuracy. It delivers this phenomenal precision without making mistakes. Number 3 is diligence. Crucially, computers never get tired, ever. Then add in massive storage capacity to hold and retrieve whatever data you want on demand. And finally, versatility, the ability to just seamlessly pivot between completely different types of tasks at the drop of a hat. This actually builds a pretty stark contrast between us and the machines. As humans, look, we are brilliant, highly creative thinkers. But let's be honest, we have some severe limitations when it comes to repetitive tasks. We suffer from fatigue. If I asked you to sit down and solve, say, 1,000 math problems right now, you're going to get tired, you're going to get bored, and your mathematical processing is just going to slow way down, which leads to errors. But computers, they have this incredible diligence. They can run for hours, days, even years without ever experiencing a drop of fatigue, maintaining that blinding speed of millions of instructions per second the whole entire time. That flawless diligence and speed, that's exactly why we rely on them for almost everything. Which brings us to our next section, early mechanical marvels. Because here's the thing, we didn't just magically jump straight from doing math on scrap paper to having microchips that can do millions of calculations a second. Way before the first electronic vacuum tubes, human ingenuity was already hard at work trying to mechanize calculation. And we can actually trace the chronological climb of this. It starts back in ancient times with the abacus, then takes a huge leap to the 16th century with the slide rule, moves to 1617 with Napier's bones, and then progresses even later to Pascal's machine. Every single one of these represents a monumental leap in offloading the heavy lifting of calculation from our brains onto physical tools. So this is our starting point, the abacus. It actually holds the title as the very first mechanical calculating device, specifically designed for counting really large numbers. And it's elegantly simple, right? It's literally just a wooden frame with some horizontal wires and sliding beads. But by manipulating these little wooden beads, ancient users could track massive quantities. They could perform complex additions and subtractions way faster than they ever could just in their heads. It was essentially the first time we successfully externalized our math. Then, if you fast forward to the 16th century, we get a pretty massive upgrade, the slide rule. This was developed by an English mathematician named Edmund Gunter. And by sliding these marked scales against one another, users could suddenly perform much more complex operations. We aren't just talking about basic addition and subtraction anymore. No, the slide rule introduced an actual mechanical way to handle multiplication and division, and with incredible efficiency for its time. And the innovations just kept coming. In 1617, another English mathematician, John Napier, invented what's famously known as Napier's bones. He's specifically built this super fascinating grid of physical wooden rods just to conquer multiplication. Basically, by aligning the rods according to the exact numbers you wanted to multiply, the device effectively reduced really complex multiplication down to just simple addition. It was honestly a brilliant structural hack for mathematical processing. Later on, we finally arrive at this absolutely beautiful piece of engineering, Pascal's machine, developed by Blaise Pascal. Now, this device was built to add and subtract, but what makes it so totally vital to our evolutionary timeline is exactly how it did it. The machine was made up of these intricate wheels, gears, and cylinders. By physically turning the dials, the gears inside would actually catch and turn the next cylinder over, automatically carrying the tens and hundreds digits. It was, quite literally, math in motion. And I think this brilliant contrast really illustrates the grand journey here. Placing that ancient abacus right next to a modern desktop, it visually pays off this incredible technological leap. I mean, on the left, you've got simple wooden beads on a wire. On the right, millions of microscopic transistors stamped onto silicon. They look like they belong to entirely different universes. But, and here is the absolute crucial point, fundamentally, they exist to do the exact same thing. They take inputs, they process them, and they give us an output. Let's explore that further in our next section, the input-process-output loop, which actually brings us so nicely to the core concept that unites literally every single machine we've talked about today. It all boils down to three really simple steps: the input-process-output loop. The machine accepts user data, that's your input. It performs operations on it during the process phase. And finally, it generates the desired result, which is your output. Honestly, it's the exact same logic as following a baking recipe. The raw ingredients are your input, the oven acts as your processor, and that delicious final cake, that's your output. To ground this whole abstract loop in a more practical way, the source material gives us a really great everyday example. Just imagine an online system that needs to verify your age. The input is simply you typing your birth year into the keyboard. Okay, the computer accepts that data. Then the process happens basically instantly inside the system unit. It subtracts your birth year from the current year to calculate your actual age, and then it compares that resulting number to 18. Finally, you get the output. The computer displays a message right on your screen saying either you are an adult or you are a minor. Input, process, output. It really is just that elegantly simple. We've seen how computers have evolved from literal wooden beads to physical gears, all the way to these electronic marvels of speed and diligence. And yet, they are all still running on that exact same basic input, process, output loop. So, as we wrap up this incredible journey from the abacus to the modern system unit, I want to leave you with a thought directly inspired by the review questions from our source text. Based on this massive, unbelievable evolution we've seen, what are the key developments that are going to define the next generation of computing? Like, will our current state-of-the-art machines one day look just as ancient to our descendants as Napier's bones look to us today? It's a really fascinating question to ponder. Anyway, thanks so much for joining me on this explainer, and definitely keep questioning the magic inside your machines.